Okay. Omar, the floor is yours.
Wonderful, thank you. Well, hello everyone, and thank you all for coming back. And I also want to thank especially Yves for his gracious hospitality and for hosting these lectures. So I want today to talk about how we can use the extended structures that I have been talking about in the last 3 weeks here in the Solvay chair in chemistry discussions, and show you how the strong bond approach, the high porosity, and the flexibility with which MOFs and COFs could be made can be now put to use to make water harvesting from air possible. And I hope by the end of my lecture today to convince you that we could do this anywhere at any time of the year. So one thing I did not discuss that I think we all take for granted, and that's the reason we have MOFs and COFs, is because we have overcome the crystallization problem. And what I mean by that is that it's relatively easy to crystallize molecules when they are linked by weak interactions. And we are very familiar with dry ice and ice, water ice. And also we're familiar with compounds such as coordination networks where the metal is linked through neutral linkers to make weak interactions, in this case, not very much different than about 90 kilojoules per mole. But it was really in the higher bond energy regime where a lot of people, I think, did not expect that you could crystallize materials, and especially not so as easily as now we can do it. So for MOFs, going to a charged linker increases your bond strength, and therefore the challenge to crystallization is much higher. It's even higher with the COFs. But I showed you methods for overcoming these challenges and elaborated on those. And thus really was the birth of reticular chemistry. It's the control of the strong bond, as supramolecular chemistry is control of the weak bond. So this then gives you durable materials that are not just architecturally stable, but also thermally and chemically stable to allow us to address real problems such as a clean energy problem. Hydrogen is the cleanest fuel. Methane is at least 50% cleaner than petroleum. And carbon dioxide, I've discussed these applications with you. Today, I want to discuss how we can bring access to clean, to drinking water. So this is a map of the world with areas that are water stressed being highlighted in increasing shades of red. So anything that is not yellow, you can think of it as being dry. And that's about a third of the world lives in water stressed regions. And I think the other aspect that's not often talked about is that even the water world has some questions about water purity. So that's also a challenge even in areas of the world where there's plenty of water. And for many countries, this is a national security problem, because when 160 countries in the world are importing their water, you can imagine that this is a contentious issue, and it represents survival of different nations as their water is being imported. Now, the UN projects that this situation will get worse. And I'm not an alarmist, but a realist, and I do believe that things are getting worse. And you can see here, even in the US, where we think the Midwest and the East Coast of the US is not water stressed, but it is, because we're using a lot more water from the underground than is being replenished. You also notice that Belgium, there's a very little dot there In red, that's Belgium. And Belgium is also expected to be water stressed because of this same reason. So, and the areas of the world where it's already, let's say, water stressed because of dry weather will continue to get worse, especially with the climate changes. Now, we have solutions to these problems, but they're not ideal. There's desalination plants that in the Middle East that produce 1 million cubic meters of water daily. But these leave behind an environmentally problematic coasts, and because of the brine and the high salinity of these large bodies of water where these plants are. It's also needless to say that this is very energy intensive process. For example, a country like Saudi Arabia spends almost 25% of its entire energy output for desalination, on desalination. So that is a massive cost. And again, you see here, like I said, we are in irrigation. We're using a lot more of the underground water than is being replenished. This is a picture that I extracted from The Guardian, where they're showing how a dam in Sao Paulo that supplies Sao Paulo with water is drying up. And as I said, the UN reports that in this case, in this report, they project that almost 5 billion people on our planet will experience water stress in the year 2050. So water is a big issue that we have to reckon with sooner or later. Our idea is that there's plenty of water in the air. In fact, there's as much water in the air as we have on our planet in rivers and lakes. So here, the estimates is that it's around 13,000 cubic kilometers of water in the air at any one time. And if you can find a way of extracting this water from air, you could bring drinking water or water for household use and agriculture to people in the world that need it. Even those of us that live in water regions where it's more humidified, one can use these materials to also harvest water from air. Now, before all of you get alarmed that Yaghi is aiming to dry our air and take all the water out of the air, I just want to say that if you were to serve each person on our planet 50 liters of water a day, you would have only used less than 0.01% of the water in the atmosphere. So we are in no danger of using up all the water in the atmosphere, and of course, water is recyclable. So nature has found a way of extracting water from air. Here's a beetle that is found in Namibia, just off the coast in the desert. And because there's fog, the beetle's back has nanoridges onto which water droplets and water can be seeded, and droplets can grow, and it can ultimately hydrate the beetle. This is how it works. It needs fog or high humidity for these nanoridges to work in this way. And so you see this often on the coast, where in the morning you have some fog, and one can use that high humidity to harvest the water from air. This process is not new. This has been known for a long time, and it's used a lot, I would say, in Asia, where structures such as this are that are constituted from nets onto which fog droplets or water droplets can adhere and then grow and then drip down and collected. It's not a very efficient way of harvesting water from air, because a lot of the water gets evaporated before it seeps down into in collection. Now, There's also the idea of harvesting water from air has been there, since 1,000 years. And if you Google water harvesting, you'll find that there are companies that will sell you things that they call water harvesters or instruments that they claim can capture water from air. And it's true for the most part. However, if you look more deeply, a lot of these, in fact, all of them do not work at low humidity. So they only work at high humidity, and they work by the cooling of air, just like your refrigerator. So they're energy intensive, and the lower the humidity, the worse they perform. So I would say that these machines, no matter what the fine print claims, they do not work below 60% relative humidity. And so our idea has been, if we can find a material, design a material that can extract water from air in the red regions of the world that you see here, then it should be possible to not just deliver water in those regions where it's most needed, but also in other regions of the world where there is water, like in some of the blue regions you see here, that are humidified, but the water is not clean. And thus my vision of, could we harvest water from air anywhere in the world at any time of the year? If we could do that, we would have utilized a resource of water that is air and tapped into it without harming our planet, since it is recyclable and then it could be used and then evaporated into the air. So how far have we gotten in achieving this vision? Well, let me talk about the challenges for harvesting water. Here's a psychrometric chart plotting the water vapor in air in grams per cubic meter versus temperature. Okay, and so you see here the lines of humidity, 10%, 20%, 30%, and so on, up to 100%. If you're at 100%, that means it's easy to get the water out of the air. Okay, that's, if you're here in these regions that are marked in this brown, then it's very difficult to get water out of the air. And let me tell you why. Let's say that I'm in a city where the temperature is 30 degrees C and the relative humidity is 20%. That means I'm over here where this A is on this chart. And let's imagine that I want to get the water out of the air using the current methods of cooling. Now I have to cool down the air all the way here to 100% to obtain 100% humidity so that I can condense the water. That means that I have to cool down the temperature down to 4 degrees Celsius. Okay, that's not practical. You can generate drinking water this way, but it will not be economical at all. And the idea is that if you could design a moth or a cough that is programmed to extract water from air, then you would have, let's say in a closed device, you could create a humidity so that because the moth can extract water from 20% relative humidity, it will eventually accumulate enough water to raise the humidity. So it's almost like taking, let's say, desert air and making it a tropical air, meaning increasing its humidity. Now, if I want to get the water out of this air, all I have to do is cool it down a few degrees, down to 26 degrees, to be able to get the water out. Much, much better prospect for extracting water from air in an economic way. So, and that's really the principle behind using moths or adsorbents for extracting water from air. So there are many things that are being investigated, many materials for extracting water from air. Zeolites, for example, polymers, hydrogels, and even hygroscopic molecules. And obviously salts. We all have experienced salts clumping up because of their water uptake from the air. Let's start here. Salts, there are three basic qualities that you need in a water harvesting material, at least three. One, and without these three together, you're not going to make a good water harvesting material, okay? So one is that you need high capacity. High capacity means that you don't have to do as many cycles to get water, okay? So the less number of cycles, the better, because each cycle, there is energy involved. You have to take the water out. And let's say in a salt, water is bound through Lewis base, Lewis acid interactions, and there you would need energy to take the water out. So I would say high capacity is very important. Fast kinetics. If the water is bound too strongly into the material, then you're not going to be able to do, let's say, those cycles with great facility, and you're going to require more energy. And third, you want to be able to extract water where it's most needed from arid atmosphere. Once you know how to do that, you could also use the same material for high humidity. So with these three basic criteria, none of these things really pan out. Okay, zeolites, they hold on to, as all of you know, zeolites hold on to, although extract water from low humidity, but they hold on to the water so tightly that it fails in these two categories. Polymers and hydrogels and molecules, they variously work, but none of them has been demonstrated to work at low humidity. And of course, salts they work at low humidity, but the rest is bad because of the strong bond that water is making to the metal in the salt. So that's where MOFs sort of are heaven sent, because you can design them, you can modulate their interior to adjust for optimal conditions for these three categories. And so just because sometimes people ask, I have a slide here to show that BASF has been scaling up MOFs in multi-ton quantities for various applications. This is one of the MOFs. I think this is MOF 5 that is being in a big barrel, being scooped up. It's a nice white powder. And they have also the ability to shape the particles for various gas storage and catalysis applications. So the way we discovered water harvesting from air was really during our studies of CO2 capture, because as I mentioned, when you're capturing CO2 from air or from flue gas, you have to also reckon with water, with the competition with water. You're also absorbing water. So we wanted to understand how do MOFs interact with water, and how does water compete with CO2? And then we found in this MOF, this is a zirconium MOF made from fumaric acid. We found that in this particular MOF, that water can be extracted at around 20% relative humidity. And this is the behavior that you see in red, a very sharp knee behavior, which in this is the power of the isotherm that I have emphasized in my last lecture, is that this shape gives you a lot of information about what's happening in the material, but also the sharper this step is, the higher your working capacity and the lower energy you'll need, because now I only need to vary the conditions very slightly in terms of the humidity to be able to harvest the water. Or I could use, in this case, and another very surprising behavior, is that we are able to extract the water out by heating to 45 degrees C. Okay, now I looked at this uptake and release behavior. One, you can extract water from air at low humidity. Fantastic. Two, using the step approach, we knew that this must be a cooperative interaction because of the shape of the isotherm, but also that we would have high, the maximum amount of, let's say, working capacity. And 3, I can get the water out by heating at mild temperatures that that sometimes you see in the desert in the summer. So my thinking was, well, maybe we could use this mop to extract water. And of course, my thinking was in the desert, let's say in North Saudi Arabia or in South Jordan, where it's extremely dry and hot during the day, and during the night it cools down. So basically, could we use a powder of this material to extract water at night? And then during the day, as naturally, the device will heat up and then water will come out and condense it. So that was the vision. And in the lab, before we go to the desert, in the lab, we did many studies on these materials because we thought, well, they may not be as stable in water, but indeed they were very stable. And you see here a behavior where we can do many, many cycles, in this case, 80 cycles without the framework being compromised. And one of the things that we observed is that after the first cycle, there is a slight drop in capacity or in the uptake capacity. But then there is a very stable performance. And that's the nice thing about having crystalline materials. So the crystallinity that we work so hard for becomes now very important. And so we then did a crystal structure of this material with a few doses of water, the initial doses of water, to find out what's happening. And indeed, when you look at we looked at both the X-ray, single crystal X-ray diffraction and the neutron diffraction, and this is what we found. We found that the first water molecules, here is the oxygen red, bind to the hydrophilic metal oxide units. So they bind tightly to those units, and they form tetrahedra, as you see here. In this particular tetrahedral pore, you see tetrahedra. In this octahedral pore, you see an arrangement that approximates a cube. And as you dose more water is added to those initial water molecules. And so we immediately realized that, in fact, that drop that we saw here must be these water molecules that are strongly bound to the hydrophilic metal oxide unit. And indeed, it's those water molecules onto which further water molecules bind and build up in the pore, as if you were building up a piece of ice inside the structure. It was absolutely fascinating. And now you can see why many MOFs could be used for water harvesting from air, because the most hydrophilic centers are going to be where water binds and stays. And in a way, protecting the framework from any degradation over a period of 4 or 5 years, which is exactly the amount of time that these materials would be graded for in a device. So very exciting. And so I wanted to show that this can work outside the lab. And so I sought the help of Evelyn Wang, who's a mechanical engineer at MIT. And there we decided to build a device this is a handheld device that employs only 2 grams of MOF. And basically the device works in the following way. It's a box, and you've got your 2 grams of MOF here. At night, you open the box, water from air goes into the MOF, fills the pores, and during the day, you close the box, and upon exposure to sunlight, obviously the interior of the box heats up. Here, as you can see, as it is heating up, the water from the pores comes out, and you can see larger and larger droplets forming. This was really exciting. This experiment was done not in this particular one, not in the desert, but in outside in Boston on a dry day, they had a humidity of around 25 to 30%. So this was very exciting, and it's a clear demonstration that you could use this moth in real life environment to harvest water. There isn't much water because we only use 2 grams of moth, but clearly you can see it forming in these panels here. Then we took the device to the desert, and now you can see visibly the bubbles of water forming on the material. So that was our initial device, and MIT folks got very excited, and they gave Evelyn a lot of money to develop that. And then I had to go my own way because I didn't get funding from MIT. So instead, we built our own next generation device where you have at Berkeley, where we have a box within a box. So our design basically has 2 boxes, and in the inside box, you have the moth. And in this case, we wanted to demonstrate that you can not just see the bubbles, but you can harvest real water that ultimately could be used and drank. So it works in the same way. The moth here takes up water from air at night. During the day, you close the outside box, and at ambient temperature, ambient sunlight, the interior heats up, water comes out, condenses on the walls, and you can collect it. We took this device to Arizona, and it looks like this, just one plexiglass inside another, nothing more sophisticated than that. And we found that you can deliver about 200 to 300 milliliters of water per kilogram of moth. Okay, that's about a small bottle of water. Okay, and you can see here the condensation on the walls of the device. This is the water that they collected from this experiment. Now, this is what you could do with one cycle day and night. At night, you take up water from air. During the day, ambient sunlight heats it up, and you get the water out. Okay, and you have a way to condense it and collect it, as you see here. That's one cycle day and night. Okay, and the moth, we found out that the moth is maintained, and we found out also that the water is ultra pure. There's absolutely no metals, no organics, and no other contaminations into the moth in the water, because the moth, you can tell the chemist amongst you that the pores are just right for water. So it's really a molecular filter for water. So there's absolutely nothing else in the water. So it's pure distilled water. And Eugene sent me a video, to my surprise, where he's drinking the water.
2, 3, action.
Cheers. Nice.
Okay, it's nice because that's
All right, ready, 2.
That's Eugene's product. It's probably a little bit bitter because it's a distilled, but to make it drinkable, all you have to do is mineralize it, just like all the water we drink is mineralized. That's easy to do, it's very routine. Now, the nice thing about moths is that once you discover a phenomena or a structure, and let's say that structure is made from expensive zirconium. Zirconium is about $160 a kilo. And so for us to be able to use this in society, we had to design a moth that's made from a very cheap metal like aluminum. And indeed, we chose this kind of linker based on our knowledge of water harvesting from those experiments. And we chose an aluminum rod structure and to make what we call Moth 303. Moth 303 is an amazing structure because it's made from a reticulation of very nice pockets, such as you see here, and they repeat throughout the structure. You'll see later that these pockets are ideally suited for water to bind, not to the metal oxide unit, but to the organic linkers, and have an ideal conditions in which adsorption and desorption can happen, high capacity, fast kinetics, and at low humidity. This aluminum MOF turned out to work much better than MOF 801, the zirconium MOF that I showed. So here's a plot comparing MOF 303, which is the aluminum MOF that we made, and the uptake from another MOF called aluminum fumarate. You can see aluminum fumarate works at 20% relative humidity, while MOF 303 works at much lower humidity. This is around 10%. And if you're really interested in 5%, it takes up water at 5%. And some zeolites and inorganic systems are shown here. Like I said before, they take up water at low humidity, but they have a problem with releasing the water or the obtaining high capacity. So clearly MOF 303 is a star here, not just in terms of its capacity, but also in terms of it being able to take up water at low humidity and at the same time, as I will show you, release it very quickly. Okay, so you can see here, this is the adsorption in MOF 303 and desorption. This is done at different humidities. Obviously, the higher the humidity, the faster the uptake. But even at 20% relative humidity, you see that adsorption is not a problem at all. And desorption, let's say at 65 degrees, can take place very, very quickly. Okay, and you can basically deliver all the water so it combines, let's say, a nice balance of adsorption and desorption, so that you can do a cycle in a reasonable amount of time. And so based on those results, we designed at Berkeley another prototype. This prototype uses what I didn't say, that in the first prototype, the kilogram prototype, we discovered that in fact we're only using a fraction of the MOF, because the MOF was put in the device as a cake. So we were only using around 30% of the MOF. The rest of it was completely unused because air just couldn't penetrate through a cake of the MOF. So here we try to address that problem by using cartridges of MOFs. Still, we're not using all the MOF, but we're using about 50% of the MOF. And so you can see now the engineering challenge that is emerging is that you want to be able to manufacture the MOF in a form, let's say a coating, that doesn't compromise its surface area while at the same time exposing all the MOF particles to air so that you can take advantage of the high surface area of the MOF. But in this particular second generation, we were accessing more of the MOF. And we did another thing here to allow us to carry out more than one cycle a day by attaching the device to a solar panel, which provides the power that we will need to push air into the material so that we can do more than one cycle. We're not relying on the day and night cycle. So once you have a power, you can use the power to push air into the MOF so that the MOF can take up the water. And when it's saturated, you can heat up the MOF to release the water. So this is unlike the kilogram device that I showed you before, the box within a box. That was completely passive, no electrification, working only on ambient sunlight. In this case, this would be more electrified to allow us to do more than one cycle a day. This is the results of the experiment. We took this device, it employed around a kilogram of MOF also, to the Mojave Desert, and you can see here the relative humidity. We measure it during day and night. You can see that at night it's more humid. During the day it's very, very dry. It goes down to 7% relative humidity. The amazing thing is that even though we have very low humidity, you're still harvesting water. Clearly you harvest water at night because it's more humid, but during the day you can still harvest water. So this was a clear demonstration that the MOF works outside the lab. And you can see here in real time the device harvesting water from air and condensing it as you see these droplets. Now, from this experiment, we harvested around 1 liter of water per kilogram of MOF, better than the passive device, but clearly not up to the capacity of the MOF. We still are not accessing all the granule of MOF. But now we are talking about significant amount of water. This is 1 liter per kilogram of MOF per day. The MOF, in this case, so far has been tested over 30,000 cycles and still performs perfectly. You'll see why in a second. And it can stay in the device for 5 to 6 years. That's what's graded for. So then basically you have a scenario where the MOF is working day after day and month after month, year after year, all because of the strong bonds that are holding the structure together. So this is MOF 303, and you can see here the adsorption is within minutes at different humidities. The desorption, let's say if you decide to desorb at 85 degrees, it happens within minutes. So that basically is telling us, if you want to commercialize this, one of the things you could do, if you don't want to do the passive device, you want to do the active device, then you can do many cycles during the day. And accordingly, we built a 3rd generation device shown here. It looks complicated, but in fact, it's not. A lot of these wirings are for studying the humidity and the temperature inside the chambers and so on. But the way it works, it has a door. The door opens and air goes in. And it goes in and it's adsorbed on modules of MOF, where we have learned now much better how to make coatings of MOF and accessing most of the MOF. Actually, the large majority of the MOF is being accessed by air. You can see here water accumulating. And here the water is being collected. So from this experiment, this device only uses 200 grams of MOF 303. And from that, you can harvest 4 liters, and depending on the conditions, dry conditions, you can harvest up to 5 liters per day, okay? So that's 200 grams of MOF delivering 4 to 5 liters of water per day. And that's, I would say, that's beginning to be very interesting for commercialization. The power use of this device is no more than the power used in some of the small appliances that you have in your kitchen. This is a countertop device. This is no larger than a microwave oven. And you have 200, as I said, 200 grams of MOF that can stay in the device for the lifetime of the electronics, which is 5 to 6 years, delivering on a daily basis 4 to 5 liters of drinking water. So we have made tremendous progress since we first discovered water harvesting. And you can see here we're approaching about 80 liters per kilogram of MOF per day. The capacity of MOF 303 should get us to 100 liters per kilogram of MOF per day. And since the MOF, like I said, can do many cycles and can stay in the device for years, then now you have the possibility of harvesting significant amounts of water and beginning to utilize water from air as a new resource for water. So that device, if we put it in the Atacama Desert, I showed you the Mojave Desert, but the Atacama Desert is the driest desert in the world. And the driest time of the year is August. And you can see that our MOF would work. If you look at the weather conditions, you look at the humidity, and you look at where the MOF is taking water, you can easily calculate how much water you're going to get at any time of the year. And so you see the MOF works under the most extreme conditions. This is the Mojave Desert. This experiment was already done. Lanzhou, Kabul, Riyadh. You can see that even in Riyadh, a dry environment, that you can harvest close to 40 liters per kilogram of MOF per day. Baghdad, New York, Stockholm, Los Angeles, London, Granada, Rome, Perth, Cape Town, Delhi. Okay, so like I said, if you could trap water from air and release it under energy efficient conditions, now the vision of trapping water anywhere in the world, humid or arid regions, is possible at any time of the year. And so again, we wanted to dig deep into where is the water molecules going in the MOF CO3. And there we work closely with the theoreticians like Laura Gagliardi and her group and Joachim Sauer. And together we did independently experiment and theory and found that in fact, I just want to remind you of the structure of MOF CO3. It's very important. This is a single pore, and then if you slice the pore in half, you can see the interior. And what's going to happen, you're going to see water binding to the NH unit in the linker as the first binding site. So we were very fortunate in that we were able to go along this isotherm and get a crystal structure for the different doses of water to see what's happening inside. And this is what you see. The first water molecule binds to the NH unit and this nitrogen, not to the metal oxide unit. And the second one to the other side, okay? And the third one is on the OH unit that is decorating as part of the metal oxide SBU. And then that's it. Those are the three, let's call them seed units. Joachim calls them carpet waters, the ones that are bound directly to the framework. And then onto those, you have additional water that later binds to those original positions, okay? And then it builds up from there. You have more and more, but only 3 that bind per unit, per pocket, 3 that bind to the framework, and then the rest of the water binds to those. You can see here that we have the water in the pore in different colors. The red color is the first stage. We call it the seeding stage, and the yellow is a clustering stage, and then the networking stage, meaning that the water starts binding from pore to pore. All of these positions were determined from single crystal X-ray diffraction. And at least for the first water molecules, theory also is good enough to show us, to also confirm or to give us the details of the water binding. But all these water molecules were located by single crystal X-ray diffraction. And here's a movie to show you. I want you to look at where the water goes, but also what's happening to the framework as a whole as the water is filling up the pore. So this is MOF CO3. This is a single channel. We're going to slice it so that we can see what's going on inside it. Okay, those are the binding pockets. It's first water, second water, third water, fourth water. And now you have build up of what I call ice fragments inside the structure. The structure does adjust as you're adding more and more water, but only by a few angstroms. So that's how the pores fill up, and that's the evolution of water into the structure. Now, based on that information, now the power of reticular chemistry is that you can build the same MOF structure, but now instead of NH units, you can have an oxygen. And now you can play with the binding energy of those water molecules. Not only that, but also you're able to adjust the position of water so that that can impact on the packing of water molecules inside the framework. But clearly, by taking the perazolate and substituting that with this furan-based linker, you can see that how we are shaping the isotherm. Okay, so we can, by playing with the ratio of adjusting the ratio of the perazolate with the furan in the same structure, you can adjust the shape or the initial step of the isotherm, okay, and adjust the humidity at which the structure could take up water from air. That's the power of MOF chemistry. And I talked to you about multivariate MOFs. Now you see that now mixing two linkers in the same structure impacts a great deal, as you see here, on where the water would be, at what humidity the water can go into the pores. And I think much more important than that is the fact that you can adjust the temperature at which water comes out. Okay, so here is the structure with the most furan, or with the, with 50% furan, 50% perazolate, and you can see that we can take up the water, the desorption temperature is 45 degrees C, while the one that is entirely perazolate is close to 57 degrees Celsius. So what I'm trying to say here is that we have the ability with reticular chemistry to not just make MOFs that are robust for water harvesting, but also you can make pinpoint changes using the multivariate approach to adjust the desorption temperature, the binding energy, and as you will see in future publications, and really pack water most efficiently within the pores, depending on how those very first water molecules go into the pores. So that's the MOFs. We have recently discovered that also COFs could be designed to have water harvesting characteristics. They're not as good as MOFs yet, but this is our first experimentation with that. This is a MOF, a COF that takes up water at 35% relative humidity. It looks very good in terms of cyclability, even though it's an imine COF. But like I said, we are just slowly getting into also COFs for water harvesting. Okay, as I said, if we serve 50 liters of water to each person on our planet, we would have used only a very tiny amount of the water that is in the atmosphere. And what we are doing from the grand scheme of things is that we're creating distributed water that is mobile and off-grid. And basically, it's like taking the wired phone and making a wireless phone. People can take their water wherever, and they can have their livelihood. They can live anywhere where they can extract the water. And it's pure, it could be used for drinking or household use. And really my dream is to have available to the world water independence for the individual, where the individual controls their water and for drinking and for other uses. So finally, I want to acknowledge my group, in addition to those that I have already mentioned in my presentation, and the funding sources. And I just want to say that it's all about control of matter at the molecular and atomic level. And I hope I showed you with reticular chemistry that we can control matter in infinite directions, in infinite dimensions, especially 2D and 3D. So therefore, taking chemistry from molecular chemistry in terms of precise and control of molecules and atoms and bonds to the infinite regimes. So as one of my colleagues said, Michael O'Keefe, who I've worked with for a long time on nets, he said there has been nothing like it in the history of chemistry, and I tend to agree. Thank you so much for your attention. And again, Yves, thank you very much for being such a gracious host. I'm happy to answer any questions.
Well, thank you very much, Omar, for this fascinating talk. And I think you really develop a fantastic technology. I mean, in terms of contribution to mankind, this is absolutely fabulous. I have, of course, a few questions, but I see that Anne has a question. So lady first.
Yes, so thank you for this fascinating talk. I mean, it's absolutely wonderful, and it makes you dream about, you know, chemistry to the service of mankind. It's absolutely beautiful. So you should go in all schools and tell that to young kids, and so that we could, I don't know, have new chemists coming to study and developing things, because it's absolutely beautiful. And so I just have a question about now the fact that it will be commercialized. So clearly, more than you, if you have so much 100 liter of 100 liter of water per kilo of MOF and etc. But then how much does your system cost? And then the next step is what, that you would have the state buying it and bringing it to the population, but then what's really the cost? This is
a lot of nice questions, and they're all very complicated, because the chemistry, as far as I'm concerned, is done, right? We have shown how you can extract water from air and deliver clean water in arid regions of the world. And the rest is just business, right?
Mhm.
So in a small company called Water Harvesting Inc., that's where that last prototype was designed. That uses, and it's fascinating how working with engineers, just changing the practical aspects of a project, they are absolutely brilliant. Mm-hmm. And working with the engineers, we discovered that taking a nitrogen, putting an oxygen there, has tremendous impact on how much water you can deliver. And so for a device that would deliver for a village 20,000 liters of water, by just doing that MTV, that multivariate MOF, I can deliver 15% more. Okay, that's 1,500 liters extra. And that's how many more people could drink. And and much more to your initial point, which is that MOF chemistry in general has been extremely attractive for young scholars to plug into chemistry. Mm-hmm. And I think what water is doing, as I experience a lot of emails from high school students, mm-hmm. And even elementary school students that see a report in their newspaper and write me about MOFs and about water harvesting. It's just very, very exciting. It's reaching into the hearts of young people that chemistry can deliver a solution. And so back to the small company, the Water Harvesting Inc. company that is here in the Silicon Valley. So they made this device. It uses only 200 grams of MOF. Okay, so the reason I said it's wonderful to work with engineers, because they found a way of making coatings by blending with polymers and coating it onto an aluminum surface to maximize the exposure of air to each particle. And if you could, I said that the theoretical limit for that MOF is 100 liters per kilogram per day. And you can come very close to that. Mm-hmm. And so that's one sort of advance that we have made that was not there before, is to blend the MOF without compromising its surface area and maintaining its molecular structure so that you can take care of those. So what is the company talking about now? They're talking about this device being in like an appliance in a kitchen to deliver 4 to 5 liters per day. In their models, they tell me that it would cost, at least at this initial stage, it would cost $1 a day to supply a family of 4 with drinking water. Okay. but that's basically the cost of electricity.
Yeah, no, but that's amazing. That's amazing.
Pardon? That's the issue.
I see it's amazing because that's the solution.
Right.
Yeah.
And so now the next thing that they want to do, they decided, well, that's one direction. The other direction is that now they're going to hire larger devices that deliver 150 liters per day. And those, the condenser mechanism is different and more efficient. Okay, so that, let's say, that can take an order of magnitude lower amount of energy because of the different mechanism of how the condenser works. So that's their next project. And then ultimately, we want to be able to have very large systems, like I said, 20,000 liters that could supply a village with water. So, do you compete with, in the electrified device, do you compete with the desalination? No. I mean, desalination is still an order of magnitude cheaper. But the advantages you get, even at this initial stage, in independence and off the grid and control of your own water, are tremendous. And in today's society, independence is everything. Individual control of your water is everything. So I would say we're doing very well. If you really want to go into parts of the world where there is no electric, you have the passive device. The passive device uses absolutely no energy aside from ambient sunlight. For each kilogram of MOF, we already demonstrated that you will have, even by only using 30% of the MOF, about 300 milliliters per kilo, okay? So, if you scale that up, more MOF, that means more water, sitting there in a corner, harvesting water. No energy input aside from sunlight. I think that that's even far more impactful than the electrified device. But we still need to work more on making that device construct more robust so that it can sit in a desert area and operate without interference. Yeah.
And then, if I may just ask, then does it mean that for you everything is done, or you still have a dream in some chemistry you would like to do in the future?
Well, you should come to my talk in MOF 22 in Dresden, because there I will talk about the future frontiers of reticular chemistry, and we're not done. We only scratch the surface. Because once a chemistry is all about control of atoms and molecules and how they bond to each other. And I think this is just the beginning. As I said, this has propelled chemistry into 2D and 3D without losing the precision that molecular chemists have enjoyed. But now you're doing it on materials that are designable, just like you would design a molecule, except you have Avogadro's number worth of unit cells per particle. And so I think this is the beginning. I did give a hint in my last lecture about materials that operate with sequences that code for specific properties. I think there's tremendous potential there. I think the other potential, Anne, is that what we have shown with the water harvesting is that you can combine the beautiful chemistry with engineering, and if you include multivariation and sequences with computer science, all being done in one laboratory. Now, when I was a student, we just made compounds. We didn't even look at their properties or their applications.
Yeah.
So, I think we all remember if we were concerned with synthesis and we wanted to study, let's say, electronic conductivity, we had to collaborate with somebody in engineering too. But now all of these, in MOF chemistry, all of these things are happening in one lab. The chemistry, the engineering of the device, and the computer science that is needed to, in the case of the multivariate systems, to get at the sequences. But also, we are developing as chemists appreciation and understanding of all these engineering models device system, whole system models that engineers use. Okay? Yeah.
Thank you. Thank you.
You're welcome.
So I see that Gabor Schuster has a question.
Yeah, thank you. Can you hear me?
Yeah, but there is a lot of noise.
So that I cannot change, sorry, because nothing is happening around. So, first of all, I wanted to thank the talk because it was really nice. The scientific part, I like it a lot. But my point is that when you solve a problem, you always generate another one. So, what is your opinion? Because the contribution you made, it's really nice, but let's say I'm not that convinced about the only positive outcome that you are. So how do you see the I don't know, the future? If you start using this kind of devices for millions of people every day, then what problem you can imagine?
Yeah, I get this question a lot. What if the glass is half empty? And in this case, let's say, I just want to make a general comment that a human civilization advances with technology, with new materials. And I made this point at the very outset. And with all advances comes other things that we have to also address. Otherwise, we will just not do anything and stay where we are. But in this case, we have been thinking about the lifetime of the material. So the material is made from aluminum, and it's made from a linker that's not exotic linker that requires complicated chemistry to make. The synthesis is very simple, and it's made in water. And everything, there's no organic solvents, and everything that you put into the synthesis ends up in the MOF. So there's no waste. And the MOF is formed as a solid. You use it for 5-6 years. And then when you're done using it and it's not, let's say, it's not up to its original performance, you can add acid to it and separate the metal from the organic, then reassemble it again in water with zero discharge. So I think okay, are there problems that are going to emerge from that? Well, I don't know. You're using water solvent, you're using aluminum, and you're using a process that's zero discharge. To me, that's progress. And you're providing water to people who really need it.
The chemical part I accept, and that was obvious that in this sense it's really great. My point is rather for the environment, that you were referring to changing the humidity of air by a very tiny amount, but it's the same for the CO2 production as well. We change it by a very, very tiny amount. It's measured in ppm, which is much smaller than this number, and still it makes huge trouble after a time. So when I start drying the environment, even in my house or whatever, some people, they put some water just on the heater or something to put some water into the air. So again, I don't want to argue with you because the technical and the scientific part is great, but I think it will raise a new question in, I don't know, 20 years or 50 years or whatever.
Yeah, I don't want to argue with you either, but your question is extrapolates, and I think all these extrapolations end up in disappointments for those who extrapolate. For example, before the invention of the automobile, people in New York City were wondering what will happen when the population increase at the rate that it was increasing to all the manures that the horses were producing. And all of a sudden, this kind of question with these unreasonable extrapolations comes up. So that means that in a few years, the whole of New York City was going to be covered with horses' manure. And now what the problem with that thinking is that it's not just an extrapolation based on unknowns, but it's an extrapolation that does not take into account human ingenuity, inventions, people solving problems. Do you know a technical problem that humans have not solved when they put their will and the resources behind it? I don't. And that's what I really want people to think about. Not to discount the power of the human ingenuity to solve problems. as we advance in technology. That's the hope for the future.
Okay, thank you.
I see also another advantage that could be indirect advantage. Generally in developing countries, often getting water, that's a task for women. And they take a lot of time for that, or the day. It's quite some hours generally to walk, to the well, to get water. And if all this time would be freed for these women, they would have much more time for education.
You know, Yves, that is a very nice comment. And I'm getting shivers because, you know, my own mother was delivering as a young girl, had to carry this heavy thing on her head. The water is heavy from the well into the village and going back and forth several times a day. And you know, you can see pictures, let's say in India, where now women can drag this barrel behind them. I mean, this is an arduous process. And I love your comment about having enough time so that they can go to school. I mean, how can you go to school after you've done this? Right? Yeah, it's I think when this is deployed, it will be a magnificent, I think, achievement, especially for those who live in these arid regions.
Yeah. So I see that there are still questions from Jean-Marc Sparenberg.
Yes. Can you hear me?
Yes.
I'm trying to activate my camera, but it doesn't work. Anyway, thank you very much for this very fascinating talk. I'm an engineer myself and quite impressed. I was wondering, you mentioned in your last slide other applications, because that very pure water could be used for other purposes, like water electrolysis. And we have a company in Belgium which is also a spin-off, but from the KU Leuven University, producing hydrogen by harvesting water. I don't know the technology they use, but I don't know whether you are aware of such use of your technology.
Yeah. No, I agree. I think you can. There are some people that have cheap source of solar energy, concentrated solar concentrators that are proposing to use water harvesting technology to extract water from arid regions and providing hydrogen fuel. Thank you for your observation.
Another question from José Monroy.
Yes, thank you, Professor, for your time. It's very inspiring. I have a question related to the last part also, when you show the tetrakis ethene cough, the last one that is
the cough, yeah.
And I think it's not completely planar, right? It has to be in 2D, but it's a little bit twisted. Do you think that if we have something that is twisted, some organic framework that is twisted, could be the replacement for a metal-based framework? Because maybe if we have something that is twisted, then the condensation of the water will be higher. Or maybe I'm wrong.
Thank you for the question. I have given up trying to predict what water will do, because figuring out what the water molecules were doing in MOF-303 completely changed my view on what is needed for water harvesting. It is so amazing, because the way the first water molecules sit in the pocket seems to have a deterministic effect on the density of water that builds up in the pore. So it's not like shoving tennis balls in a basket. It's really, water is an intelligent being that, depending on how it sits, it determines the whole construction of the water in the pore. And so your question is really right on. If I can cause kinks on the internal surface of the moth or the cough and then I have the right atoms there, nitrogen and oxygen and the things that you need, then maybe I can impact how the water, the density of water that builds up in the pore, and therefore impact on the performance of the system overall. By the way, your question is so fascinating. It reminds me of, again, more credit to the engineers, is that very tiny changes that you make in terms of capacity. Let's say you, by having these kinks in the pores, you increase the uptake by 5%, which to a chemist is almost nothing, right? 5%. It doesn't sound, you can't even publish it. But to an engineer that does system modeling, they can tell you that 5%, because you are cycling so many times, that adds up to a lot of water. So every little bit change, every little bit of change that you can make in the internal surface will impact on the system. That's really the biggest discovery that we made in terms of connecting the chemistry to the system. So are coughs going to figure prominently in water harvesting? They will. This was our first cough, and it only has 1 nitrogen, and you can see already that it's taking up water at humidities of 35%. So that tells us make coughs that have more heteroatoms. Okay. Yeah. So that's what we're working on now. Yeah, you're welcome.
Then one last question. And what about the separation of heavy water from water?
I don't know where I saw this, but I probably shouldn't. I should just say that I don't know whether it was a paper I reviewed or I saw this in somewhere. I can't remember. But there is interest. I know that there is interest in using MOFs to separate D2O from H2O. Yeah.
Yeah. Okay.
That's a good idea.
Then last question from Géraldine Chanteux.
Can you hear me?
Yes.
Okay. Thank you for this wonderful talk. I mean, it was not the first time I was hearing you, but yeah, it's always fascinating to see the progress and so on. I was actually wondering if there is any impact on the air pollution. So depending on the place where you are taking and you are experimenting your device, is there any effect in your system, in the MOF viability, in the MOF, I mean, when you want to recover it and so on, and if it makes it more difficult?
You know, I thought of this potential problem years ago, and we were sort of anticipating it, but the device has been functioning in the California atmosphere, which is sometimes nasty in terms of the fires and the dust. But we have not seen degradation of the performance at all. So I think in reality, if you really want to make sure you don't run into these problems, you can always use filters like air filters, right? Which is, you know, they're not very expensive. You can get very inexpensive air filters that will, but we have not. That's a good question. We have not seen any degradation of performance. Yeah.
Okay, and then the next question is that, okay, you have like a certain like level of humidity in air, and is there like a maximum humidity that you can reach before the MOF is degrading or the system is not operational anymore?
No, that's the beauty of this MOF. MOF 303 is based on a rod SBU, and the rod SBU shields the metal oxygen bond. The other thing is that you have one water molecule, the third water molecule, is also further protects the metal oxygen bonds. And so we don't see degradation in MOF 303 at all. And if we did, the company would not license our technology. Yeah, so it's a very nice, I would say, coalescence of the chemistry with the ability to do something. productive with the structures. That, and the other thing is that don't forget the power of the cough, because the cough backbone, I showed you, you can make carbon-carbon bonded backbone. And now we know the secret. We know the secret for water harvesting. We know exactly what it requires. So if you're really interested in this problem, you should be working on coughs with heteroatoms. Okay, and then you don't have the metal. Yeah.
Okay, thank you so much. But yeah, nowadays I'm working in MOF systems, but anyway, it's another story. But thank you very much for this fascinating talk and these talks. And
thank you. Yep.
Okay, so I don't see any more questions. So, well, Omar, for sure, I would like to thank you warmly for your beautiful lectures. That was very inspiring to us, and I'm really looking forward to meet you. I think in next October, at least we will meet in person at this moment. So thank you so much.
I'm looking forward to it, and thank you very much. And
you're very welcome.
Everyone for listening and their questions. Yeah. Okay. Take care.
Bye-bye.
Bye-bye.